for today's interaction, the asymptotic analysis of norms in integer partition, and I decided to look at specifically those partitions with distinct parts. So if you look at the presentations we've had with the previous few presenters, we've looked at various combinatorial structures, including set partitions, trees, permutations, and now I introduce us to integer partitions. And we've also had terms like exact formulas, recursive formulas and stuff. So in today's talk, we look at asymptotic analysis. So, and just for introduction, I would want to let us know what an asymptotic analysis is. The basic definition here is that if you have, say, two functions, f of x and g of x, we say that these two functions are asymptotically equal if, so we say f of x and g of x are asymptotically equal if the limit of their quotient is equal to 1. So yeah, my notation seems to misbehave. So we give it as f of t is, f of x is asymptotically equal to the notation again, sorry. So f of x is asymptotically equal to g of x. Yeah, that's the notation. I'll try not to use this as much and probably stick just to the slides. So yeah, so that's it. We said that these two functions are asymptotically equal if the limit of their quotient as x approaches infinity is equal to 1. So let's get into basic definitions of what an integer partition is. So an integer partition is a way of expressing an integer n as a sum of positive integers. For example, if you have an integer 4, we can have it, you can express it as 4 or 3 plus 1 or 2 plus 2 or 2 plus 1 plus 1 or all ones. And now the count is 5. There are 5 ways in which you can express 4 as a sum of positive integers. And this we say that the partition of 4 is equal to 5 and denote it by this. There is a geometric way to show this using the Young diagram. You can show that, for example, if you take the partition 3 and 1, you can have this diagram where we have 3 boxes on the first row and the second row gets the second box. So you can have them as dots, and we call that a Ferrez diagram. So if you look at the corresponding number of partitions, say for 1 is 1, 2 is 2, 3, we have 3 of them. For 4, there are 5, like we've seen. For 6, there are 7, and so on. You can check this on the online encyclopedia of integer partition, integer sequences. So if you look at this particular sequence, it keeps increasing rapidly. So we don't have an exact formula to tell what these partitions are. And what we now do is asymptotic estimate. So I'll define the second term, which is the norm of a partition. So Schneider and Seals in 2021 defined the norm of a partition as a product of the parts of the partition. Previously, they independently have worked with the norm partition, just not having the definition norm partition. It was formally defined in this particular paper. And for example, the partition 4, these are its norms. So the first partition, which is just 4, the norm is 4. The second one, it's 3 times 1. The third one is 2 times 2, which is 4, 2 times 1 times 1, or 1 times 1 times 1. So giving us, these are the respective norms. At the start of this year, Walter and William published this paper. There is a preprint, 2023 preprint. On this paper, they showed that the norm lacks a limiting distribution. And now in this particular work, we look at the log of the norm. And the reason as to why the norm has no limiting distribution, first, if you look at how rapidly growing our sequence is, you can imagine what happens to its norm. It grows, in a more rapid way. So basically, for you to bring that to bring that data closer, you introduce the norm. And the second reason is that norm in itself is a multiplicative parameter. With integer partitions, we use additive parameter. So it makes more sense to consider an additive parameter, and introducing the log to this particular product, it becomes the sum of the logarithm of these particular parts. We also have, beyond the ordinary partition or the standard partition, we have other types of partitions that we call lambda partitions. Basically, we call it a lambda partition if the members of that particular partition are drawn, say, from a set lambda. In this case, where lambda can be the set of prime numbers, squares, or whatever attribute you choose to pick. So if you look at the same example for standard partition, we have 5 of them. But if you only pick the primes, we only have 2 plus 2. That's the only one where we have primes. If you only pick the squares, then you can only have 4, 1 plus 1 plus 1. The distinct, which doesn't appear here, but it's what we want to focus on today. If you look at the distinct parts, it's parts with multiplicity 1 that, the parts do not repeat. So we have 1, we have 2. Those are the only 2, because here 2 repeats, 1 repeats, 1 repeats. So we only have the first 2 where we want to, if your lambda is, you want to look at distinct partition. And there has been a mention of generating function, and this is the approach we use. So it's a symbolic method so with generating functions, we want to take our sequence, the sequence that we create of these partitions, and look at what particular power series it corresponds to. So in our case here, if you look at this sequence, at this series, so the first term of the series, it's 1, which you can see here. You can have z to the power 0. So it's the coefficient of z to the 0, z to the 1, the coefficient is 1, z to the 2, the coefficient is 2, and so on. If you look at these numbers, here it's 1, 2, 3, 5, 7, 11. This is the same sequence we have here. 1, 2, 3, 5, 7, 11, 15, and so on and so forth. So instead of now thinking about those numbers, we can now think about this particular series, and this is the interpretation of the terms that, z to the n encodes or partition of n. For example, here to z to the 4, it represents z to the 4, z to the 3 plus 1, and so on. If you look at this, these are the partitions here. So we've encoded our count of partitions in this particular series. We can represent this sum as a product. It's called the Euler form, and here is a way to do it. So these are step-by-step derivation. Because of time, I won't look at the details, but basically, this is what we have from, this what we have from this particular sequence, that there are 2 ways of, z to the 2, the partitions of 3, there are 3 of them. So we classify them together and then sort them. Let's put together, in the sort, and then we can have product where the parts are sorted in this way, and we can have this particular form, the Euler product. So what about the lambda partitions? For the lambda partitions now, this generating function, basically you are taking, for example, here, the first one, it's just the odd number. So if you're dealing with the odd numbers, it means you do not include the second factor here. So it's the first one and the third one. And how do you show that? So it's the powers that you have here. You have 2m minus 1. So that's the odd part. You can do the same thing for even, for prime. So just picking parts where, you know, factors that are prime. And then for distinct parts, it's a little bit more interesting, because if you look at these, you just want, you know, one appearing just once. So you pick 1 plus z to the 1 and then remove the other part. If you want to appearing just once or not appearing, then it's 1 plus z squared and then you remove the other part. So basically it's an inclusion-exclusion principle that we use to derive the formula for distinct parts. And how do we go about this? Okay, before that, I would like to mention that once you have a generating function, then you can tell the method of attack. So in our case here, if you look at our generating function, one of the easiest approaches one would easily imagine is probably singularity analysis, where you factor out where the poles are. The poles is where, you know, the denominator here gives you a 0. So if you equate this to a 0, you get where the denominator is a 0. If now you look at it as a quotient, we call it a pole. So you factor out the pole and then you can analyze that. But now here is a problem that every term of the product here introduces a new pole. So basically we can't factor it out. So by that, now we seek a method which is called the saddle point method, and we shall come to that. And one of the things that makes it easy for us now to do this asymptotic estimates, I should have given here the generating function for distinct parts. This is not for distinct part, but it's a kind of general. So we use the Meinardus scheme, which gives a set of conditions to some Dirichlet series. And this Dirichlet series is a series that's that basically is associated with our function f of z. So this Dirichlet series has to satisfy 3 conditions. One, it's analytic continuation. The other one is growth bound. And the other one is a decay of power series. So this is the process for the saddle point method. And if you want to learn more about the saddle point method, there is the analytic combinatorics book by Flajoy and Sidgwick. Here it is. So that's the book you refer to, and the things we talk about are in chapter 8 of this particular book. So this like the Bible of analytic combinatorics. Flajoy is like the father of, is actually the father of analytic combinatorics. So this is a very comprehensive book, and most of the arguments you can find them in this particular book, and it's available for free online. So this is the process. So we have our generating function, and we can tell what the coefficient of the term z to the n is. And we denote it by 2pn, which we've already seen that the coefficient of z to the n, it's the partitions of n, the number of ways to partition n. And now with this one, we can use the Cauchy's coefficient formula, which is also known as the Cauchy residue theorem, which gives us this expression. And now what we are attacking is this integral form of this particular formula. This is the one now we get to attack. So number one thing is to substitute this z with this particular exponent. And why do we specifically choose this condition? It's because of this. We want to analyze it in the unit circle. So here as r approaches 0, this particular item here, I mean the radius approach 1. So that's why we choose this particular expression or choice of z. And now if you factor in if you substitute these particular expressions, this is what it becomes. You can factor out e to the n, R. So if you factor that out, anything that doesn't relate to T basically, because we are integrating with respect to T, we can factor it out. This is what we have. And now with the saddle point method, the thing is we want to identify a path. And if you choose carefully a path, then you can, if you carefully choose that particular path, it means that you can be able to apply the saddle point method to estimate this particular coefficient. And how do we choose this particular path to get the saddle point? Because there is a particular point we need. The way to choose is just to select an appropriate R. If you find an appropriate R, then that R will be our saddle point, and that's how we use the saddle point method. This now the key steps. We try to, so if you look at this particular function, f of our z, it's still too big. We introduce logarithm, which is a standard practice. If you've introduced the logarithm of this, we denote it by that. And thus we can say that basically if the log of this is this, then it means this particular function is the exponent of this particular thing. That's the equivalence there. So nothing much is happening here, just substituting them back, and now this is what we end up, just algebra, no tricks up to this point. So we need the saddle point equation, and for the saddle point equation, we take this value here, differentiate it, partially differentiate it with respect to t at t equal to 0, and then equate it to 0. That should give you the saddle point equation. So, and this saddle point equation is where we get the value of R. So this, this saddle point equation should also give the relationship of now this n to R. So remember, R is a saddle point which we carefully choose, and then we get the relationship to n, and our n now takes us to the integer n. The next step is to expand around t equal to 0 at basic Taylor expansion. You can proceed up to the term. So the point at which you stop the expansion is the point at which the terms start to tend to 0. So in our case here, this particular, that derivative starts to tend towards 0. So we can terminate it here by having this as an error term. Then, so we are left with this particular thing and an error term. But this particular part now, if this particular part also gives us something we call an identity we call Gaussian, that gives us the Gaussian approximation if extended to infinity. And now we are able to estimate in this form, and our formula simplifies to this. So if you want to now get more refined output, now the task is for us to refine R and f of R. And what is f of R? Basically, it's the logarithm of our generating function. This particular function in our case here, it should be 1 plus z to the m, because we're dealing with distinct parts. So if you find that, if you get the logarithm and then that product becomes a sum from, if you find the logarithm of that generating function, then that gives you an f of R. We also need to find the second derivative and the third derivative. And what happened to our first derivative here? It was swallowed by this, because n is equal to negative of f prime of R. That's why the first derivative is missing here. It's because this one has canceled it out. So it simplifies to that. So once we have these functions and their derivatives, the next thing to do is for us to transform them. And the reason for Mellin transform is for us to get where the poles are, where are the singularities of this particular power series. Where do we get the singularities? And once we have the singularities, then we can employ the converse mapping theorem. This is an argument that comes that I quote in the work by Leibniz and his co-authors. So this, he said, the central advantage of the Mellin transform is not necessarily the transformation itself, but moreover the converse mapping, where we consider the singularities of the transformed function, providing the asymptotic expansion. So that's why we use the Mellin transform, and the Mellin transform is just an argument similar to say the Laplace transform. So where we have the Mellin transform and the inverse, just like the Laplace. So here we introduce some interesting model, which is not quite new. So instead of now dealing with the lambda partitions in the sense where, they appear, how about not check the conditions of those lambda partitions and give weights to those particular parts? So we now transform our work from just lambda partitions to weight and partition. And for weight and partitions, now we have a partition of n given by L, and then we define the multiplicity. Multiplicity is the number of times that term appears. For example, if, just to take us back here, so if you look at this one, the multiplicity of 2 here is 2, appears twice. The multiplicity of 2 here is 1. The multiplicity of 1 is 2. The multiplicity of 1 here is 4. 1 appears 4 times. So in a lambda sequence, for example, if you're dealing with plain partitions where every term appears k times, so your lambda here would be 1, 2, 2, 3, 3, 3, 4, 4 times, and so on and so forth. So we can have those sort of sets of lambda sets. Now, instead of dealing with them in that nature, why not give weights to those particular parts? So, and then just have the standard or the ordinary partition with weights attached. So this is how we define the weight function. So the number of times this particular item appears, that would be the weight. And now we can have a sequence now focusing on the number of times an item appears. So if you look at the weight on the whole partition, because now this is the number of multiplicity. Now the weight on the whole partition, this particular partition, will be the weight of k times its multiplicity, obviously. It's the function of the multiplicity of the weight of k, and k now it's from 1 up to, the number of terms you have infinity. Next, we have the random partition model. So remember, our partitions are very random. And here now, what's the partition of L basically is given by the weight divided by the partition of n in L. And now the log of our norm, we can denote it by, the log of the norm, I have given it as omega n of L, but in some instance, I'll just denote it as omega n. So the next thing now, using the generating function approach, we have a bivariate generating function. The same thing we've had, it's only that now this one this BK should be up here. Sorry, but there's some sort of correspondence. When you have it here, when you have it as a power here, it behaves in a similar manner. So you can see this some sort of confusion. This one should be here because we are choosing the number of times this particular variable, this particular item appears. So it can be now that this appears 5 times, it works in a similar way. So if you do the binomial expansion of this now with your BK as a power here, if you do a binomial expansion, you start to look at, you see how now the weight function, we can look at how these particular functions respond, and now we can pick the weight function from this one, which is BK, the number of variables or distinct variables. For example, how many times does K repeat? If K repeats BK times, so that's what we mean by BK, and this is the multiplicity of BK. It's a little bit different. The weight function is a little bit different if you're dealing with say, unrestricted partition, where we have the generating function 1 divided by 1 minus this one. This particular thing will be different depending on what we get here from the binomial expansion. So notice that when we have bk equal to 1 here, we just have the normal, the classical distinct part. So where it's a subset of the natural number. So in this case, I give an example of, say, partitions of 6 where we have distinct parts, and then we are giving weights. For example, we can have k repeated k times, but these k's are distinct. For example, if it's 2 and 2, one of the 2's is red, the other one is black. So it's both of them are 2's, but we consider them as distinct if maybe they are labels or colors. So we are trying to exponent this to, you know, a higher degree expression. So if you have, say, 6, how many ways do you choose? 6, 6 distinct ways, it's 6. So here notice we just have 6, but we can have 6 red. One of them are red 6, a black 6, a blue 6. They are distinct even when it's the same item. So it's the same 6, but distinct in 6 ways. This is one of the ways you can distinct them. It can be that you have just 2 distincts, in the sense that you have just 2 colors, red and black. So 1 appears twice as red and black, 2 appears twice, 3 appears twice. You can have all these sort of variations. But now in our case here, we've picked bk, the number of variants to bk, that's 4k, so that every k appears k times. There are k distinct k's. So this is the partition. If you want to see the weight, that's how you using that formula. There are 6 of them. And the norm is just 6. The norm here is 5 times 1, which is 5, and the weight is 5. So our omega 6 here is log 5 because we are dealing with norm. Omega 6 here is log 8, and so on and so forth. So we can look at how the probability of getting a log 6 when now we have these things. Remember that for the partitions of 6, we should have, we should have 6, 5 plus 1. There's also, say, 3 plus 3, but 3 plus 3 is missing from this because you're only considering the distinct one. So 3 plus 3, in that case, 3, it means we have to choose 3 ways and another 3 ways. So it's a little bit different here. That's why the aspect distinct here could be a little bit confusing because we have like 6 repeated 6 times, and then still notice that now if you repeat a black 6, if you use 6 and 2 of them are black, it means black is no longer distinct. So distinct on 2 levels. Distinct in the sense that the colors are different even though the number is the same. So the weight, the total weight is 25. Here you sum this up, 6, 5, 8, and another 6 here, it's 25. And the probability of getting a log 6 here is now 6. You can get a log 6 from this. You can get a log 6 from this. So it's 6 plus 6 divided by the total possibilities, which is 25. The possibility of getting log 5. Log 5, if your omega 6 is log 5, the probability is 5 over the total 25, and so on and so forth. Notice that if we are now dealing with classical distinct parts, that now we don't have the coloring or stuff. So 6 appears just once, 5 just once, 4 once, 3 once, and the rest. Then the total weight would be 4. This one would be 4 because we would have just this, that, and that. And all would have weight 1, weight 1, weight 1, weight 1. I hope that now clarifies the issue. So the first thing for us to do is to get the probability generating function. So remember, first we started with a moment generating function, and now we are at a probability generating function, which we get in this manner. So the probability generating function is now given as a quotient, where the denominator here is Pn and the numerator is given here. And that's the same argument basically we've been having here. It's only that now we are giving it in a structured way, in the manner we do the analysis. So this is the argument behind the example. And now our aim is to look at the distribution of omega n. So once you have the probability generating function or this particular expectation, if around u equal to 1, we get the distribution which is of interest to us. If you differentiate it once and then you want to around u equal to 1 after the first derivative, that gives you the mean. After differentiating twice, around u is equal to 1, you get the variance. If you continue that way, and that is called the method of moments, the same one that Walter and Wills used to determine that this particular that the norm parameter has got no desirable distribution. So these are ways to go about it. That this expectation, this probability generating function, this particular this one gives us the distribution. So we keep it at the distribution, we can go ahead to get the mean and the variance. So the first thing we do is to normalize our variable. And once we normalize this variable now using our method, the saddle point method, and now the arguments of these probability generating functions, which calls for us now to analyze this particular, the numerator just as we do with the denominator, and later have a moment generating function, another moment generating function now that's given here. The moment generating function, if you look at it, it closely mimics the probability generating function. So if you analyze this particular thing with an appropriate choice of mu n and sigma n, which in normal cases, we would have it as the mean and variance and the standard deviation respectively. But in our case, we choose not to, to compute the mean and the variance, because if you choose them with an appropriate choice, it doesn't have to be exactly the mean or exactly the standard deviation. Anything within an appropriate choice gives us our distribution. We can use that to normalize our variable and we get the distribution. So we analyze these coefficients here and we show that it converges to a nice limit. And again, we use the saddle point method, like I said, the Mellin transform, and these are some of the advantages. I'll quickly run to the results. This is what we get. That for this particular function, we get the Gaussian distribution, and we give the approximation of our mu n and our sigma n squared, which give us very nice functions here. So the interpretation of this is that we get a normal distribution after centering and scaling. We have some examples. If you have the standard partition with distinct parts, your BK now becomes 1 because we don't have various variable distinctions. Every number appears just 1. So our Dirichlet series becomes the Riemann zeta function, and basically this is what we have as our asymptotics for mu n and sigma n squared. There is comparison with some results we have for unrestricted case. Here it's partitioned into powers. Whatever powers, this is what we have. If we have just the squares, you can see the behavior. This is what we call the asymptotic estimate, the behavior. It's n to the third log n. If you're dealing with just squares, if it's cubes, the growth keeps, the growth rate decreases. If you have primes, so for prime partition, our Dirichlet series does not obey the Meinardus scheme, but now Naina has some work already done on this. So we borrowed the argument in this particular paper. You can check it. Actually, it was his PhD it was in his PhD thesis. So I used that particular approach to estimate for prime partitions, and we give it as an example. For plain partition now with distinct parts, this what we have as a plain partition. We can have it in this form, the geometric representation. If you have it as cubes, this one will be a 3D diagram, unlike what we had as a 2D. So basically that's what we have, and that's the growth rate. So we were with the asymptotic estimate, we are looking at the growth, or the behavior, the distribution, and this is what the outputs usually look like. Thank you for your attention. Now, because of time, I will take questions.
Okay, thank you so much, Dennis, for the nice talk. Okay, so it's open for questions. You can just go ahead if you have questions. Remember, you have to always unmute before you ask. There is Master Shah. You can just go ahead, Master Shah. Hey, Master Shah.
Hello, Dr. Naina. Hello, everyone.
Hey.
Hi, hello, Dennis, my brother.
Hello, Master Rachel. Nice to see you.
I am happy to see you. Dennis and I were both students of Dr. Naina, the role model. Naina is, I don't have any word to explain. Naina, I don't know. I don't have words to explain. Naina, you made us good and good.
Thanks, Master Shah.
Dennis and me, we had 2 wonderful years together at Stellenbosch. Just we call it is brother because we are a student of Naina. Naina is a good father for us. Just one question. Actually, most of the works are related to mine because I also worked on asymptotic approximation. But when you do integer partition, for instance, if you consider the integer partition of 4, P of 4 is 5. Do you have a general formula for any integer partition? For instance, if you have an integer n, can you say that the integer partition of n is n plus 1, or do you have any general formula? That is my question. Thank you.
Okay. Thank you, Mr. Rachel. We do not have an exact formula for any of these estimates. These partitions also do not have any sort of recurrence relationship that we use. So that's why we go the asymptotic way, where we start to look at the behavior of their growth. So we can estimate, we can give an approximation, and the asymptotic estimate becomes more and more, closer to the exact thing or more accurate as n becomes bigger. So that's why we do the asymptotic estimates in this case.
Cool. Are any other questions?
Yes.
Olivia?
Okay. Thank you so much, Dennis, for the nice talk you've given us. So I just have a comment on your statement, the statement you've just made, that these partitions, like there's no recurrence relation for the partitions. So I and my student, we've been trying to, actually we've worked a little bit with these partitions, and we actually realized that these integer partitions are in bijection with the run sorted binary words of length 2n, meaning these binary words have n zeros and n ones. Like for example, if you go back to the table that you had with the partitions, I don't know if you can share your screen again. Yeah, with the partitions.
Yeah.
Yeah, so now like for that first partition, for 4. So in that case, the corresponding run sorted binary word of length to n would be having 4 zeros and 4 ones. Then for like the second last one would have a binary word like 0, 0, 1, 1, 0, 1, 0, 1. So the bijection was that each part in the integer partition corresponds to the number of zeros and ones in the run of the binary word. So that was our bijection. And we had some recurrence relation that seemed to work, and we were able to give a combinatorial proof for it. So I think now, since these two are in bijection, then I think we can say that we have now a recurrence relation. But I'll still agree with you that it wasn't easy to find a closed formula or a generating function, a nice generating function for this. And I've learned from your talk that, yeah, we can just get estimates by doing the asymptotics and so on. So it was very nice to hear from you. And then I also saw you had some probability concepts. So we also did some work around like finding the expected value for the number of descents. And then from this, we got some formula that had n factorial somewhere. And I've got from your talk that we can actually simplify this expression further by doing some asymptotics. So yeah, it was nice. Thank you.
Thanks, Olivia. Well, by the way, I think there is obviously a lot of possibilities to get a recursive formula for the number of partitions. That's but the closed formula, depending on what you mean by closed. If you take some algebraic, I don't know, modular form type of stuff, then there is a closed formula. I think that was a formula by Ken Ono and something that came out recently. But in a sense, those are all useless. It's like not natural at all. But I think, yeah, so there's no easy formula. I think that's the way. But there is definitely a recursive formula that's known a long time ago. I think every one of us will be able to come up with one. But yeah, just to clarify that.
Okay.
Yeah,
Thank you.
and also thanks for that, Naina. And also while dealing with when we are dealing with these partitions, when we are counting, if you look at this expression, for example, we see some sort of pattern that we use to determine the, how the weight function look like. So there's some sort of recurrence that gives us the number of counts. So, but now for the general old thing, it's where it gets different.
Okay, are there more questions? Well, it doesn't seem to be much. So, oh, there's Fufa. Fufa, can go ahead.
Yeah, just one question. Thank you, Dennis, for your nice talk. You have defined weight for integer partitions, and I